there is one more thing I would like to tell you guys about angular momentum before we go on to a different subject, okay? And that is on this area of what happens if you need to add up two different angular momenta, right? So for example, suppose you have two particles and they each have some spin. Okay, so, whoops, here, this is meant to be one particle, particle one, and here's particle two. And they each have some spin about their axis. Okay, and so this is in a spin state of S1, M1. And this is in a spin state of S2 and M2. And so the question is, how do you combine them? What can we say about the total angular momentum? So this is important when you have more than one particle. And it's also important if you want to combine spin and orbital angular momentum. Right? If you want to add those two things up to get the total spin plus orbital angular momentum. Okay, so this then goes by the general theme of addition of angular momentum. And so that's the title of a section in the textbook. And so what I want to present to you now is a particular example where we can see how it works. And so that example will be the case of two particles, each with spin a half. So I'm going to show you how this works. And then after that, well, I can't prove it in general, but I'll show you, I'll tell you how it generalizes to the arbitrary case of any spins or any L. Okay, so let's think about this example, okay, with two particles and they each have spin a half, okay? And now, suppose we want to characterize what is the combined spin state of both particles. Well, one way we could do that would be just to list the quantum numbers of both particles inside of one big ket, okay? And so we could write that ket as S1, M1, S2, M2, like that, okay? And so for sure, this would have all the necessary information to describe what's going on with both of the particles. For sure, this would work. Now, it's kind of a long notation to write out all this stuff, right? There are different ways we might shorten the notation, right? So we might shorten the notation by, well, we know that S1 and S2 are each a half, right? That's the example I'm giving. So we might say a half M1, a half M2. Or we might decide, well, we don't even need to write out the halves because I'm just telling you in advance that they're both spin a half. So we could just write it as M1, M2. Or we could write the states as up, up, right, to indicate that they are both pointing up, right? So this means M1 equals a half and M2 equals a half, right? And so, any of these things would be a perfectly good notation to describe the spin state, okay? And so now we could say, how many possible spin states are there, right? Well, the first particle can be up or down. The second particle can be up or down, so that is to say spin up or spin down, okay? So there are 2 times 2, right? That's 4 possible spin states, right? So I could say, let's make then a list of all the spin states. And I could write them in this shortest way as up, up, and up, down, and down, up, and down, down. Okay, that is 4 states. Okay, so 4 states. All right, so now what do we know about these 4 states, right? Well, we have an operator for the spin of one particle. So there we have an operator S1, that is the spin of particle 1. And that is equal to Sx1, Sy1, Sz1. Okay, and there's also an operator S2, that is the operator for the spin of particle 2. And this is a vector of operators. So it's Sx2, Sy2, Sz2. Okay. And we know what each of these operators does to any of these 4 states. Okay, so the spin operator, the operator S1, it cares about particle 1. It just doesn't care about particle 2. Okay, and so that means if we have SZ1 and it acts on any of these states, it only looks at what's the spin of particle 1. Okay, so this thing acting on up, up, that's equal to a half h bar times the state up, up. Okay, and it's a half h bar because this thing is m of particle 1 times h bar. Okay, and similarly, SZ1 acting on up, down equals a half h bar times the state up, down, because it doesn't care about what the second particle is doing. It only cares about the first particle, okay? And so it just gives you the eigenvalue of plus a half h bar, because that corresponds to the spin state of particle 1. And likewise, SZ1 acting on down, up is negative a half h bar times down up, because it cares about the down, that's particle 1. And SZ1 acting on down, down is minus a half h bar times down, down. Okay, so that's for SZ, okay, the Z component of the spin. Now there's also an S squared for particle 1, okay? And so here, maybe I'll make another column over here. Okay, so there's an S for particle 1 squared. That's a funny looking notation, isn't it? Right? It's S, and then the 1 in parentheses means particle 1, and then the 2 outside the parentheses means squared. Okay, so this thing acting on the state up, up, okay, that equals 1/2 times 1/2 plus 1 times h bar squared times that state up, up, okay, because it reports the eigenvalue of S squared associated with particle 1. So that's the 3/4 h bar squared, right? That's S times S plus 1 times h bar squared, right? Associated with particle 1 times the state up, up. And likewise, S1 squared acting on up, down is 3/4 h bar squared times up, down. And the same for the other two. Whoops, what am I doing? Down, up is 3/4 h bar squared down, up. And S1 squared acting on down, down is 3/4 h bar squared down, down. Okay, that is all for the operator S for particle 1. Okay, now we have, whoops, the same kind of story for operator S2, which cares about particle 2. So I could write out all these things, but I don't want to because that's kind of boring. So I could write out all these things, right? But now they all depend on what's the second arrow instead of the first arrow, okay? So it cares about whether the second arrow is up or down, and it doesn't care about what the first arrow does. Okay, so now comes the question, okay? The question is, what can we say about the total S? The total S, which is S for particle 1 plus S for particle 2. Right? This is an operator, right? So, you know, we've had other sums of operators before in this semester, several times, right? So for example, you know, when we did raising and lowering operators, it was some combination of the position and momentum operators, right? And so here we have an operator that's a combination of S1 and S2, okay? And so now we want to say something about what are the eigenvalues and eigenstates of this combined spin. Now, the combined spin, it's still an angular momentum, okay? And so what do we expect, right? Because it's an angular momentum, we expect to find eigenvalues and eigenstates of SZ, and S squared simultaneously. And, we expect that because we've found that works based on just the commutation relations for any angular momentum. And so stands to reason it should work for this combined angular momentum also. Okay, so we think we should be able to find the eigenvalues and eigenstates of the combined SZ and the combined S squared simultaneously, but not the combined SX and the combined SY, right? That those things should be incompatible with SZ. Okay, so the combined SZ, spin vectors, it's a vector of operators, but still it adds up like other vectors. Okay, so the combined SZ is SZ for particle 1 plus SZ for particle 2. Okay, the combined S squared, that is the vector S1 plus the vector S2 squared. Okay. So this is S1 squared plus S2 squared plus S1 dot S2 plus S2 dot S1. Okay, so let's see if we can find the eigenvalues and eigenstates of these two operators. So if we want to do this, we should let each of these operators act on the 4 states that we know about and see what they do to the 4 states that we know about. Okay, so we know about these 4 states, right? Up, 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 down, etc. Okay, so let's first say, what does SZ do to each of those 4 states? Okay, so SZ acting on the state up, up, okay, that is SZ1 acting on up, up, plus SZ2 acting on up, up. Well, we know each of these things, right? SZ1 acting on up, up is a half H bar times up, up, right? Because it cares about the first spin. SZ2 acting on up, up is a half H bar times up, up, because it cares about the second spin. So we just add those 2 things. Okay, so that makes H bar times up, up. Okay, now SZ acting on up, down, that's SZ1 acting on up, down, plus SZ2 acting on up, down. So that's a half H bar up, down, plus negative a half H bar times up, down. So that is 0, right? Those two things cancel. Okay. Similarly, by the same story, SZ total acting on down, up is also equal to 0, right? It goes the same way. And SZ acting on down, down is negative H bar times down, down. Right? Or if I wanted to write all of these things compactly, I could say SZ acting on the state M1, M2 is equal to SZ1 acting on M1, M2 plus SZ2 acting on M1, M2. So that is M1 H bar times M1, M2 plus M2 H bar times M1, M2. So that is M1 plus M2 H bar times the state M1, M2. Okay, so the M quantum numbers, they just add up, right? In just a simple way that you might guess that they would add up, right? So this combination is not so surprising, right? This combination is just what you might guess. Okay, good. Now comes the harder one. Okay, what about the S squared? So suppose we want the operator S squared. Okay, so as I wrote out before, right, this is S1 plus S2 dot S1 plus S2. Okay, so this is S1 squared plus S2 squared plus S1 dot S2 plus S2 dot S1. Okay, so now if we look at the last two pieces, right, these are the operators written in different orders. So let's think for a minute, do they commute, right? The answer is yes, they do commute, right? It doesn't matter what order they're in because they act on different spins. They don't really communicate with each other because one does something to a state based on what's the particle 1 spin, and the other does something to a state based on what's the particle 2 spin, and those two things don't interact. Okay, so this is just equal to S1 squared plus S2 squared plus 2 times S1 dot S2. Okay. Now, S1 dot S2. Okay, I guess we could keep expanding that. So that's S1 squared plus S2 squared plus 2 S1x S2x plus 2 S1y S2y plus 2 S2z plus S, whoops, excuse me, that's a 1. S1z plus S2 Z. Okay, now we want to know what all of this stuff does to one of our states. Okay, how does this operator operate on one states? Okay, so let's try it. Okay, so if we want S squared acting on up, for example, okay, this is S1 squared acting on up, plus S2 squared acting on up, plus, here, I'll do the Z thing first because it's easiest. 2 S1Z, S2Z acting on up, plus 2 S1X, S2X acting on up, plus 2 S1Y, S2Y acting on up. Okay, we good so far? All right. So these are 5 things to calculate. Some of them are not too hard. Okay, well, so for example, we know what S1 squared does to up, right? We figured that out way back here. S1 squared acting on up makes 3/4 h bar squared times up. So 3/4 h bar squared times up. Okay, now how about S2 squared acting on up? Well, okay, it does the same thing. It cares about particle 2, but particle 2 has the same S of a half. All right, so this is also 3/4 h bar squared acting on up. Okay, now what about this other thing? Okay, here, I'll make my scratch paper. Scratch paper is down here. Okay. We know SZ2 acting on up is a half h bar up. What about SZ1 acting on SZ2 acting on up? All right, so that's SZ1 acting on a half h bar times up. So that is 1/2 h bar times SZ1 acting on up. That is then a half h bar squared times up, like that. Okay, so this then gives us plus 1/4 h bar squared times up. Oh, and there's a 2 in there, in front of there too. So it's actually 2/4 h bar squared times up. Okay. Now, what about SX? SX? What do we do with SX, right? Well, let's remember back to when we just have one particle. Okay, so I need more scratch paper. Okay, here's more scratch paper. Okay, what if we just have one particle in a state like up? Okay, and we have Sx that acts on it. Well, that's easier to think about if we use our notation like 1, 0, right? Remember that 1, 0 means 1 times the up state plus 0 times the down state. Okay? So Sx acting on that in matrix notation is 1/2, oops, there's no cat there, 1/2 H bar times the matrix 1, 0, 0, 1, right? This is the matrix representation of that operator times the column vector 1, 0. Let's do the matrix multiplication. This is 1/2 H bar. On the top, we get 0 times 1 plus 1 times 0, 0. On the bottom, we get 1 times 1 plus 0 times 0. That's 1. So this is 1/2 H bar times the down state. Okay, so that means, whoops, what am I doing here? This is not a Z, that is an X. Okay. Yeesh, okay, that is an X. All right, does it make sense to you now that I wrote an X there? Okay, much better. So now suppose we have Sx for particle 2 acting on the up state. Okay. Sx for particle 2 cares about the spin of particle 2. So it changes the spin state of particle 2 in the way we worked out right here. That is, it multiplies by 1/2 H bar and changes the spin state of particle 2 from up to down. But it doesn't care about the spin of particle 1. It just leaves the spin of particle 1 the way it found it. Okay, so this is 1/2 H bar times the state up, down. Okay, now what if we have Sx1, Sx2 acting on up? Okay, this is equal to Sx1 acting on 1/2 H bar times up, down. Okay, the 1/2 H bar is just a constant, so we factor it out. So it's 1/2 H bar times Sx1 acting on the state up, down. Okay, now we know what Sx1 does to the state up, down. It cares about the first spin. Okay, so when it finds that the first spin is up, it multiplies the state by 1/2 H bar and flips the up to a down. It doesn't care about the second, so it just leaves it the way it found it. So we have now 1/2 H bar squared times the state down, down. So this is what we need to go into the fourth term right here. the XX term. Okay, so we get plus 2 times h bar squared over 4 times the state down, down. Okay, we good with this stuff? All right. So now let's do the same thing with the YY term. Okay. So with the YY term, well, I'll repeat the same kind of calculation that's right on this scratch paper. Okay, so on this scratch paper, let's see here. I'll copy this and paste it. Oops. I forgot. Wait, I did this yesterday. I forgot how to do it. Oh, here it is. Duplicate. Okay, good. There it is. Okay, so what if we want SY? What if we want SY acting on this state? Okay, this is the same kind of thing, but we have a different 2x2 matrix. Okay, and the 2x2 matrix is a half H bar 0 minus I 0. Okay, so now if we do this matrix multiplication, what do we get? Okay, we get that this is a half H bar. Okay, on the top, there is 0 times 1 minus I times 0. That's 0. On the bottom, we have 1 times I plus 0 times 0. So that's I. So this gives us a half H bar times I times the down state. Okay? So the SY operator acting on the up state gives us a half H bar I times the down state. So when the SY2 operator acts on up, up, it gives us a half H bar I times up, down. And when you have S1Y acting on S2Y acting on up, up, that is S1Y acting on a half H bar I times up, down. So this a half H bar I factors out. And then there's S1Y acting on up, down. So that gives us a half H bar I squared times the state down, down. And I squared, we know, is -1. All right, so this is negative a half H bar squared times down, down. Okay, so that tells us the last term. Okay, so the last term then is going to be negative 2H bar squared over 4 times the state down, down. Okay, so what do we get? Okay, we notice that the last two terms cancel each other. Okay, there's this thing and this are negatives of each other. They cancel. So now there's everything else is something times the state up, up. Okay, there's 3/4 plus 3/4 plus 2/4. Okay, that's 8/4. That's 2. So this all is equal to 2 h bar squared times the state up, up. Okay, good. That agrees with my notes. All right. Now, the nice thing about the number 2 right here, we could interpret this 2 as being a 1 times 1 plus 1. Okay, so it looks like S times S plus 1. And we'll say, well, this state looks like S equals 1. Okay, so it looks like, well, so far at least, it looks like that 2 spin halves are combining to make a spin 1. But that seems reasonable. Let's keep going now and see what happens with the other states. Okay. So this is S squared acting on up, up. All right. So have I convinced you, by the way, on this thing? Okay. You're sort of good with that, all right? Here, I'll tell you that by the same argument. Similarly, what about if we have S squared acting on down, down? Okay, that is, the same story works there too. That is also 2 h bar squared times down, down. All right, that's not the hard one. Okay, now, what about, let's next try, what is S squared acting on the state, S squared acting on the state up, down. So once again, that is, well, we can write it out, 5 separate operators. Okay? So that's S1 squared acting on up, down, plus S2 squared acting on up, down, plus 2 S1z, S2z acting on up, down, plus 2 times S1x, S2x acting on up, down, plus 2 S1y, S2y acting on up, down. Okay, let's figure this out. Okay, again, 5 terms. The first one, S1 squared. You know about that, right? We know what S1 squared does. It multiplies things by 3/4 h bar squared. The same with S2 squared. That also multiplies the same state by 3/4 h bar squared up, down. Okay, what about the next one? Okay, so when SZ2 acts on up, down, it multiplies by -1/2 h bar. right? Because up, down is an eigenstate of SZ2, right? And the eigenvalue is negative a half h bar. Right? Then when SZ1 comes along and acts on this thing, right? It multiplies by positive a half h bar because it cares about the first spin. Right? So it multiplies by positive a half h bar. And this all is multiplied by 2. Okay, now what about with the x's now acting on this? Okay, so what does SX2 do to the state down up? Okay, well, again, let's go to our scratch paper. If we had only one spin, did I say down up? I meant up down. Okay. What if we had only, yikes, what am I doing here? If we had only one spin, we could write that as 0, 1. SX acting on that, that is a half h bar times this matrix times 0, 1. That is a half h bar times 1, 0. So that is a half h bar times the upstate. Okay, so that tells us that if there are 2 spins, we have the SX operator for spin 2 acting on up, down. It multiplies by a half h bar and flips the second spin from down to up. And then if we have the X for spin 1, that operator comes along and acts on this thing. That's SX1 acting on a half h bar up, up. That's a half h bar times SX1 acting on up, up. And we already know what SX1 does to up, up, right? It multiplies by a half h bar and flips the up to a down. Right? So this is a half h bar squared times down, up. Okay, so with that result from scratch paper, we can say this is plus 2/4 h bar squared times the state down, up. Right? Now, we're getting there. All right. Now, what else do we have? We have the same thing with the y's. Okay, I'll copy my little scratch paper again. I remember how to do that. Here. Duplicate. Okay. So here, if I do the same thing with the y's. Okay. SY acting on down. It's all very similar to what we had before, but we just have to watch out for the plus and minus signs. Okay, so here we have 0, minus I, 0. Okay, so if we multiply this out, we get let's see, on the top, it's 0 times 0 minus I times 1. That's negative I. On the bottom, I times 0 plus 0 times 1. That's 0. Okay, so that means we get this extra factor of negative I, not positive I. So S2Y acting on the down state, so this is a Y, acting on the up down state gives us negative a half H bar I times up. And if we have S1Y, S2Y acting on all this stuff, okay, then this is S1Y times acting on negative a half H bar I times all this stuff. Okay. And so that's negative a half H bar I S1Y acting on the up state. And what is this, right? S1Y acting on that state multiplies by a half H bar I, right? Not negative a half H bar I. Okay, here's the one place where the signs are a little bit tricky. Okay, so this is, we already had the factor of negative a half H bar I, and now we get a factor of a half H bar I. And the negative I times the I cancel. So this is a half H bar squared times the state down up. So if I put this result from scratch paper into the calculation, there is a 2/4 H bar squared down up. Okay, so now let's add up all this stuff. Okay, for the first three terms, these are things times up down. Okay, so we get 3/4 plus 3/4 minus 2/4. 3/4, but that's 6/4 minus 2 is 4/4, so 1. Okay, so that is H bar squared times the state up down. And then the last two terms don't cancel. Bummer. All right, so now that makes H bar squared times the state down up. Okay, and similarly, we have S squared. I'll tell you what you get. If you let this act on the state down up, right? And that comes out to be H bar squared up down plus H bar squared down up. Okay, by all the same argument, right? I just don't want to repeat it all. Okay, so now we can look at these things and say, these are not eigenstates, right? An eigenstate, they're not eigenstates of S squared, okay? An eigenstate of S squared is a state such that, you know, if S squared acts on it, you get just a number times the state you started with. And that is not true for the state up down. And it is not true for the state down up. But even though these things are not eigenstates. We can take linear combinations of these two states and construct eigenstates. Okay, so let's do that. Okay, so I'm going to take linear combinations of the state up, down, and the state down, up. Okay, one linear combination could be 1 over root 2 up, down, plus 1 over root 2 down, up. This is a root 2. Okay, another linear combination could be 1 over root 2 up, down, minus 1 over root 2 down, up. Okay, this kind of combination is called a symmetric state, right? And I'll write that as chi-symmetric. Okay, it's symmetric because up, down, and down, up come in equivalent ways. Okay, and the second one is called an anti-symmetric state because up, down, and down, up come in as negatives of each other. Okay, so now let's let S squared act on those states. So if S squared acts on the symmetric state, that gives us S squared acting on 1 over root 2 up, down, plus 1 over root 2 down, up. Okay, that is 1 over root 2. Okay, what is S squared acting on up, down? That is h bar squared up, down, plus h bar squared down, up. Okay, that's what we already figured out. Okay, now what is S squared acting on the second term, on the down, up, right? It's the same thing, right? So it's all this stuff times 2. So this is equal to 2 h bar squared times the symmetric state itself. Okay, what about S squared acting on the anti-symmetric state? That is S squared acting on 1 over root 2 up, down, minus 1 over root 2 down, up. All right. So that is 1 over root 2. We have h bar squared up, down, plus h bar squared down, up, and then minus the same thing, minus h bar squared up, down, minus h bar squared down, up. This is all just equal to 0, which is equal to 0 times the anti-symmetric state. So this is also an eigenstate of S squared with eigenvalue equal to 0. Okay. So now let's summarize our list of states, okay? If we want to make our list of states, our old list was up, 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 down, down, up, and down, down. Okay, but now I want to make a new list of states. In the new list of states, it's still up, up, and down, down. But instead of those other things, I'll replace them by the linear combinations, chi-symmetric and chi-antisymmetric. And now I'm going to recopy the new list, but arrange it differently. Okay, I'll say the states, I'll put up, up, chi-symmetric, and down, down. Okay, and then separately, I'll write chi-antisymmetric. And now we can say, what is the eigenvalue of S squared? For up, up, the eigenvalue of S squared, we figured it out way back here. For up, up, and down, down, the eigenvalue of S squared is 2h bar squared. Two h bar squared. For down, down, it's 2h bar squared. For the symmetric state, it's 2h bar squared. For the antisymmetric state, it's 0. Okay. What about for the eigenvalue of SZ? Okay, for the up, up, we found the eigenvalue of SZ is h bar. For down, down, the eigenvalue of SZ is negative h bar. For the symmetric state, well, that's a combination of up, down, and down, up. Each of them has an eigenvalue of 0. Okay, the SC eigenvalue is 0. So the sum also has an SC eigenvalue of 0. Likewise, the difference has an SC eigenvalue of 0. So this now is what I've been trying to get to for the last hour. Okay, so let's see how to interpret all of this stuff. Okay, if we look at this first set of 3 states, we'll say this is a triplet of states. Okay, and in this triplet, it looks like S equals 1. Okay? Because all of these eigenvalues are S times S plus 1 times h bar squared, right? With S equals 1. Okay. And likewise, down at the bottom, this is what people call a singlet of states, meaning just one state. And it looks like S equals 0, right? Because this 0 is S times S plus 1 times H bar squared with S equals 0. And then for the eigenvalue of SZ, this is MH bar with M equals 1. Here it's M equals 0. Here it's M equals minus 1. Right? And that actually goes along with the S equals 1, right? Because when S equals 1, M should go from negative S to S in steps of 1. And that's exactly what it's doing. Okay? And likewise, down here, this is MH bar with M equals 0. And so we know that S equals 0, M has to be from negative S to S, so M can only be 0, right? So that all works out, okay? And so then we can say that the combined state, this combined state, I'll write it in another color, we could interpret this as S equals 1, M equals 1. And this state is S equals 1, M equals 0. And this state is S equals 1, M equals negative 1. And this state down here, this is S equals 0, M equals 0. So this then is how we combine the two spin halves, okay? So the general conclusion of this is that 2 of spin a half can combine to give an S equals 1 triplet or an S equals 0 singlet. Okay. So the 2 spin a half, that means 4 states, right? Because each of these can have 2 possibilities. So this is 4 states. And the S equals 1 triplet, that's 3 states, where the S equals 0 singlet is 1 state. So that's 4. Okay, so it properly accounts for the 4, right? The counting all works out. Okay, so that took us an hour to do for the simplest case, right, of 2 spin halves, okay? Let me just tell you how it works for other spins that combine, okay? So following the same principles, we'll say, in general, if we have spins S1 and S2, they combine to give everything from S1 plus S2 down to the absolute value of S1 minus S2 in integer steps. So for example, spin spin 1 and spin 1/2 give a combined 3/2 or 1/2, right? Because S1 plus S2 is 3/2, and the absolute value of S1 minus S2 is 1/2. Okay? And if you count the states, spin 1 is 3 states, spin 1/2 is 2 states. So if you combine them, that's 3 times 2 equals 6 states. Okay? And spin 3/2 is 4 states, and spin 1/2 is 2 states. And if you add those up, 4 plus 2 equals 6 states. So that balances. And it's not obvious that it always balances, but in fact it does, right? And so there are theorems about this, that the counting always comes out right. Okay, so the same is true for orbital angular momentum also. And the same is true for spin and orbital angular momentum. You can combine spin and orbital angular momentum. For example, if you have an electron in the hydrogen atom, okay, then it has a spin of 1/2, and it has orbital angular momentum of L. And so the total angular momentum is L plus 1/2, or absolute value of L minus 1/2. And if you have a proton also, so if you have a proton and an electron in the hydrogen atom, the proton has spin 1/2, the electron has spin 1/2, and the orbital is L. So you want to combine all 3 of these things. So the total angular momentum, if you combine 2 of them and then you add on the third one also, that is L plus 1, or L, or L minus 1. And the counting, again, works out. And there are profound mathematical reasons based on group theory that kind of justify all this stuff, but that's way beyond the scope of what I'm teaching here. Okay. So This is a general rule. It also works in a deuteron. That is a proton and a neutron together in a nucleus. And this happens in nuclear physics in general, all kinds of nuclei. Okay, so that is my story about addition of angular momentum. And you can read more details in the textbook also. And for practice, this is included in one homework problem. So I just posted a new homework, homework number, what are we up to, 8, I guess, which is now posted on the Google Drive. And it is due on 2 weeks from today, April to 20th. Okay, so please take a look at that, and it will have different things to practice with about spins, and there will be one small problem about this addition of angular momentum. Okay, I will stop for here, answer any questions if you have, and otherwise I'll see you guys on Thursday.